Alright guys, last video. Let's go through and see what we can come up with. Again, this is a past AP problem. I want you to go through. We should have already gone through and seen what you can do, so this is just going over that with you. In many organisms, glucose is oxidized by carbon dioxide and water as represented by the following equation. Okay, so this is basically our combustion reaction that occurs in all living creatures to use sugar to make energy. Okay, a 2.50 gram sample of glucose and an excess of oxygen were placed in a bomb calorimeter with a heat capacity of 8.52 kilojoules per degree Celsius. The initial temperature of the calorimeter was 21.3 degrees Celsius, and once the reaction went to completion, a final temperature was recorded of 25.9. So part A asks us to calculate the magnitude of Q, the thermal energy change, when 2.5 grams of glucose is combusted. So how do we do this? Well, this is our Q equals MC delta T, but the difference is we don't have mass in our C, so we're actually going to get rid of mass, and it's just C delta T. So Q is going to equal our C, which is 8.52 kilojoules per degree Celsius, times our change in temperature. So we went from 21.3 to 25.9, so we're going to subtract those two values, final minus initial, and we're left with a change of temperature of 4.6. So the first thing I want you to do, and I'm going to make you pause the video throughout this, I'm sorry, I want you to stop and somebody explain, why did the temperature increase? I want you to understand what that actually means. So why did the temperature increase? Alright, so hopefully the first thing somebody mentioned is that the reaction is exothermic. Anytime we see a temperature increase, we automatically know it's exothermic. But hopefully that is not where we stopped. That is not all we should be able to do. The next thing I want you to be able to do is explain why the temperature increased. And that comes down to that bond energy we talked about. Remember, if it's exothermic, what that actually means is our products have less potential energy and our reactants have more potential energy. Okay, and what that goes back to is our little heat curve that we have, and it should look something like this. Okay, where our reactants are up here, products are down here, and that difference in energy is what is being released. Okay, now what does this mean in terms of temperature? Why did temperature increase? Well, we lost potential energy. That potential energy turned into what? Turned into kinetic energy. And remember, kinetic energy is what we measure when we're measuring temperature. So if we had an increase of kinetic energy in the bomb calorimeter, the temperature is going to increase. Now, also what I want us to think back to is, what does this have to do with bond energy? Okay, hopefully we're saying that our reactants have a weaker bond. They're less stable, weaker bonds on average, and our products have stronger bonds on average and therefore are more stable or stronger. So these guys have weaker on average bonds. These guys have stronger on average bonds. So hopefully we're kind of putting all those pieces together. Now, back to our problem. So we have our 8.52 times our 4.6. And we get our Q value with proper sig figs is 2 sig figs, just because of our change in temperature is 2, is 39 kilojoules. Okay, and the reason it's kilojoules is because we have kilojoules divided by degrees Celsius times degrees Celsius. Okay, next part of the problem, B. What it asks you to do is to calculate the energy in kilojoules per mole. Okay, anytime we see kilojoules per mole, even though it's not calling it that, we are basically calculating molar enthalpy. Okay, kilojoules per mole, molar enthalpy. How do we get that? Well, we're already in kilojoules, so that makes our life pretty easy. But now we need to get it into moles, which means we need to know how many moles this guy is. So we take our 2.50 grams of glucose, which we go back up and grab glucose, is our C6H12O6. Okay, which is going to have a molar mass of 12.01 times 6 plus 1.01 times 12 plus 16.00 times 6, and we have a molar mass of 180.18. So we set that up in our handy-dandy train tracks, which of course I can't draw a straight line, but that's okay, you guys get what we're doing, per 1 mole. Okay, and we take our 2.50, divide it by our 180.18, and we have 0.139 moles with proper sig figs. Okay, now how do we get it in kilojoules per mole? All we have to do is take our 39 kilojoules and divide it by our that should be 0.0139. Divide that by 0.139, and we get an answer with two proper sig figs of 2,800 kilojoules per mole. Okay, now it is looking for delta H, and so this is important. You actually need to include the sign here. Up here, it was just looking for magnitude, so it's just looking for the number. Down here is where knowing whether it's endothermic or exothermic comes into play. So delta H for this reaction, and notice this sign right here just means standard. We're in our standard state, okay, which really doesn't mean much. Is going to be a negative 2,800. Okay, and again, the negative is because it is exothermic. Okay, check out question C. This is a question I just asked you a little while ago. What does this tell us about bond energy? And explain why this reaction is exothermic. Okay, well, our bonds of our products are stronger than the bonds of our reactants. Therefore, potential energy is released as kinetic energy, turning it into, or increasing the temperature. And it's the reason it is exothermic. So really what they're looking for is you to understand bond energy is our reactants are on average weaker than our products, or our products are stronger on average compared to our reactants. Okay, let's check out part D. Using the table below, calculate the theoretical value of delta H for the combustion of glucose. Okay, so we're given all of our steps of our reactions here, which actually, if you look at it, these are also standard H values. So there's two ways you can do this. You could either take all of these reactions, add them up, and cancel them out to make our original reaction, or you could just take your delta H values and plug them in. Either way, I'm going to rewrite the reaction down here. So we have C6H12O6 plus O2 going to CO2 plus H2O, and it's already balanced up here, so I'm just going to go grab our coefficients. Our coefficients are 6, 6, and 6. Okay. And again, you have two ways so you can do this. You can take our three reactions, rearrange them, add them up, cancel out, whatever you do to the reaction you do to delta H. Or you can just take them and plug them into our products minus reactants, which is what I'm really going to do because it is the more straightforward one. So CO2 is negative 390. Whoops, if I can write a 3. Negative 390 times 6. Plus water is 6 times 290, negative 290, excuse me. So that's our products minus our reactants, which is our glucose, which is 1 times negative 1280, plus 6 times oxygen, which is, of course, in its standard state, so 0. So we go through and do the math. 6 times negative 390 plus 6 times negative 290. And we're left with negative 4080 minus negative 1280. Okay, and we add those numbers together. And we are left with a delta H of negative 2,800. Okay? Okay, now let's look at part E. Part E, I'm assuming I must have written this at some point in time or edited it because it does not make sense with the original problem. It says the accepted value and experiment value do not agree. If the calorimeter leaked heat energy to the environment, would it help account for the discrepancy between the values? Explain. So our values are exactly the same. Okay, I'm not sure if maybe we typed something in wrong or maybe it was just I edited it poorly. It wouldn't surprise me if that was the case. But regardless, let's just pretend, okay, that this number instead of 2,800 is actually negative 2,900. Okay, let's just pretend the delta H is higher, the actual delta H is higher than the one we calculated. So would the calorimeter leaking explain why that is the case? Well, your answer is yes here, because if the energy is leaked, what does that do to our calculations up here? Well, if energy is leaked, it means our temperature change is going to be less than it should be. Meaning we got a 4.6 degree temperature change, but it should have been higher. But some of that energy escaped out into the atmosphere and didn't get a chance to change the temperature of the water in the bomb calorimeter. Which means this number should be higher, our Q should be higher, and when we divide by our moles, our delta H should be higher. Okay, so just so you can kind of see that. We will go through more problems, and you have a bunch of practice problems from here to work on. And I will be back on Monday, so if you have questions, make sure you write them down, put them off to the side, and we will answer any of those questions that you have. Okay, thanks guys. I look forward to seeing you again.